Last up, complex 4. So complex 4 takes the electrons from cytochrome C and gives them to oxygen. Here I've shown you the half reaction that's happening here, but what we should understand is that a total of 4 electrons are being given to a molecule of O2 to produce 2 molecules of H2O. Complex 4 uses a wide variety of redox centers to do this chemistry. We have 2 heme cytochromes, so cytochrome A, cytochrome A3, and then new to us, we have copper performing redox. So 1 copper atom making the copper center B, and a pair of copper atoms making the copper center A. On the right-hand side, I'm showing you how these are arranged, with copper center A near the matrix, and the rest of the redox centers near the inner membrane space. How do we get those 4 electrons eventually to oxygen? Well, I'd like to talk through this a little bit because it's the first time that we see an iron center performing a 2-electron reduction. So 2 of the electrons that move through these redox centers are stored at cytochrome A, heme A3. So 2 electrons of 4 total are stored here. 1 electron is stored by copper center B. It can go from copper 1 to copper 2. This gives us 3 total electrons that are going to be used eventually to reduce oxygen to water. We need a 4th electron, folks, but you see we've kind of maxed out our capacity at the 2 redox centers surrounding the water. So interestingly, this last electron is stored at this tyrosine radical. So 1 electron is here. Because tyrosine structure can do resonance, an additional electron can be stabilized through the resonance. So 1 electron from tyrosine, 1 electron from copper center B, 2 electrons from heme A3, all given to oxygen to create 2 molecules of water. That is how we have flow of electrons ultimately to oxygen. Now, if we have movement of electrons, we should understand that the charges of these redox centers are changing. And if the charge changes, we're going to have conformational change occurring. Conformational change occurring results in the changing environments and pKr changes, which allows for proton pumping. So complex 4 also does proton pumping. 4 protons are pumped and directed to this oxygen to make 2 molecules of water. An additional 4 protons are pumped through those R groups into the inner membrane space. And that is the electron transport chain, folks. But before we leave, let's try to kind of connect our understanding of what's happening with all this electron movement to proton movement and energy, okay? So we saw that electrons were coming into the electron transport chain through NADH, through FADH2, and also potentially NADH from glycolysis. We saw that as these electrons were moving from redox center to redox center, there was energy being released. I'll throw us back all the way to one of our first slides today real quick. This slide here. We saw that the movement of electrons through complex 1 releases 70 kilojoules. We saw the movement of electrons through complex 3 releases about 40 kilojoules, right? If all this energy is being released simply by electrons moving through the electron transport chain, where is that energy going? Let's keep in mind, folks, that the inner membrane space has a high concentration of protons, and the matrix has a low concentration of protons. This means that as we are moving protons from the matrix into the inner membrane space, we are working against the gradient. We are moving protons from low to a high concentration gradient, which requires an input of energy, right? So as electrons move through the electron transport chain, they release energy. We can think of that energy as being used to create the proton gradient. The energy literally powers the movement of protons across the matrix. Across the inner membrane, from the matrix to the inner membrane space. So we are part way to understanding why NADH and FADH2 are considered high energy molecules. At least for now, we can leave knowing that the energy released by movement of electrons from these redox cofactors is stored in the proton gradient. We'll see more next time we're together. So what did we see together today, folks? We saw electrons moving from low to high reduction potential, releasing energy that is then stored in the proton gradient. We saw how redox reactions can lead to charges changing in a protein. These charges will lead to conformational changes due to repulsions and attractions that drive pKr change and proton transport. We also see a bunch of different types of cofactors and how they can do different types of electron transfer. 1 electron transfer or 2 electron transfer. And I'll leave you with this cat meme. Thanks, everyone.